What I'm going to talk to you about today is getting computers to do mathematics. So let's work out what that means. So yeah, I should say, firstly, thank you very much to the friends for giving me this opportunity to speak. So what happened to me in 2018, I turned 50 and I started to contemplate the idea that perhaps I could be replaced by a machine, right? Because this is in the news now. AI is going to take all our jobs. And so I think it's a very interesting question as to whether AI could take my job. And I guess there are parts of my job that AI most definitely could not take because, I mean, part of my job is doing things like teaching and outreach. And I'm not going to be talking about them at all. But what I'm really interested in is the research aspect of my job. And so in 2018, I was an algebraic number theorist trying to prove new theorems in mathematics, because that's what we do over in the maths department, or at least what some of us do. Certainly what many of the pure mathematicians do is they try and make mathematics bigger, and they try and understand it better. And so now this is a slightly strange situation, because I've said that the question is, can I be replaced by a machine? But of course, everybody knows that computers are extremely fast at doing mathematics. So, for example, if I just yank this window here from my other monitor, then what have I got here? I've got this is just a bog standard computer algebra system there, and so that can do calculations very quickly. So if I just mash my keyboard and make a gigantically large number there, and then I multiply, where's the multiplication symbol? There it is. And then I multiply it by another gigantic number there. So if I had to do that on pen and paper, that would take me several hours, possibly even all day. But if I just hit enter here, the computer just prints out the answer immediately. And I have no reason to believe that that's not the correct answer. So there's an example of a computer doing mathematics much, much, much quicker than a human could ever do. And so you kind of wonder so what's actually the question, right? Maybe why haven't I been replaced by a machine already, right? If computers are so good at multiplication. And the reason is, of course, that research mathematics isn't about multiplying large numbers together. Research mathematics is about something else. And so really, I think my job is to try and to explain to you what exactly I am doing over there in South Kensington that computers apparently can't do so well. And so what I want to try and explain is that mathematicians prove theorems. And an example, so probably the most famous example of a theorem, the only theorem that ever comes up in pub quiz, for example, is the Pythagorean theorem. And so this says that in a right-angled triangle, in a right-angled triangle, you square the lengths of the two small sides, and you add up those numbers, and you get the square of the length of the biggest side. So there's quite a famous mathematical theorem. And the thing I want to stress is that we've got this computer that's very, very good at multiplying large numbers together. It's probably very, very good at checking that a squared add b squared equals c squared if you give it possibly very, very large numbers a, b, and c. But the problem with Pythagoras' theorem, if you want to try and prove it with a computer, is Pythagoras' theorem is true for all triangles, right? Every single one. And there's infinitely many triangles. And so whilst you can sort of try and check Pythagoras' theorem, we could take that previous triangle and measure the sides and check Pythagoras' theorem for that triangle, to 2 decimal places. We're never going to be able to prove Pythagoras' theorem for all triangles if all we've got is a computer that can just can multiply and add numbers together very, very quickly. So you see, proving a theorem is a different kind of skill to doing a calculation. This is the problem. So to prove this theorem, we need some kind of a mathematical proof. And the mathematical proof of Pythagoras' theorem is not a big calculation. It's a different kind of mathematical object. So we've seen that computers can certainly do calculations. And what I want to talk about in this chat is the question of whether computers can do proofs, whether the computers can do mathematical proofs. And so first of all, let's sort of take a step back. Let's not do any experiments yet. Let's take a step back and let's try and understand the question a bit. Let's try and figure out, what's actually going on here. What are all these people in the maths department doing all day, every day? They're generating proofs, and what do proofs? Well, many of them are generating proofs. And what does a proof of Pythagoras' theorem look like? And the proof is it's a finite amount. I mean, you can go to Euclid and you can. It's the last theorem in Euclid Book 1, or the last but one theorem in Euclid Book 1. So you can go and find out what a proof looks like. The ancient Greeks knew what a proof looked like 2,000 years ago. So the proof is a step-by-step sequence of logical arguments, and the only thing you're allowed to use is the rules of logic and the axioms of the system that you're currently working in. And in this case, the axioms will be the rules of geometry. And if you don't know what the rules of geometry are, then if you go back to Euclid, you see Euclid wrote down extremely carefully exactly which rules he would be using. So he wrote down a big list of axioms which were allowed, and then he writes a step-by-step sequence of logical arguments, and then at the end of it, the conclusion of the logical arguments is that Pythagoras' theorem is true. That's what a proof looks like. That's what the proof of Pythagoras' theorem looks like. But actually, that's what every mathematical proof looks like. You start off with a mathematical puzzle or problem, and it might be a statement that's true for like all numbers. And so you can't check it with a finite amount of calculations, but you do this logical argument, and you come up with a proof of this statement. So a proof is a step-by-step sequence of logical arguments using the rules of mathematics. And one thing that was observed in the maybe even in the 1950s, 40s, before really there were sort of viable computers at all, viable digital computers at all, is that going through a mathematical proof there's a lot of similarity to running a computer program. Because a computer program, if you've ever written a computer program, it's just a sequence of commands, and each command is processed by the program using the rules of the programming language which the program is written in. So a proof is a big list of logical arguments following some rules, and a computer program is a big list of commands also following some rules. So there's formally quite a similarity between this concept of a mathematical proof and a computer program. And indeed, by the 1950s, there had been some formal statement that proofs were equal to programs. And now you have to say very precisely what a proof is, very precisely what a program is, and then you can prove this theorem. It says proofs are the same thing as programs. So I don't want to prove Pythagoras' theorem, but I'm going to give you one slide of mathematics, which is going to be a proof that there's infinitely many prime numbers, because this is, again, another very old proof. But the reason I'm still harping on about proof is that really proofs are at the heart of what I want to talk to you about. So if you're really not interested in mathematics, you can sort of zone out for a couple of minutes now. But let me talk about the reason that there's infinitely many prime numbers. Prime numbers are the building blocks of numbers when it comes to multiplication. Every single number is a product of prime numbers. For example, 15 is not a prime number, but it's 3 times 5. And 3 times 5, you can't factor them anymore. 3 times 5 are prime numbers. So 3 and 5 are prime numbers, but there's infinitely many prime numbers, and this was known 2,000 years ago. And in fact, it's equivalent to say that there's infinitely, another way of saying there's infinitely many prime numbers is just saying for any number you like, however big, I claim that there's a prime number that's bigger than it, right? If we could prove that, then there must be infinitely many prime. If there were only 100 prime numbers, then you just if there's only 100 prime numbers, you take the biggest prime number, and then you take a number bigger than that. You add 1 to it, and then say, well, now there's no prime numbers bigger than that number, right? So to prove there's infinitely many prime numbers, we just have to prove that there's a prime number bigger than an arbitrary number given to us. So that's the theorem I'm going to talk through. This is the one slide of mathematics. For any natural number n, there's a prime number that's bigger than n. And the proof has got a brilliant idea in. And the proof I'm going to explain here, the brilliant idea is to just come up with a very large number out of the blue. And that number is, you take the number, we've been given a number n, you take the numbers from 1 up to n, you multiply them all together, and then you add 1. And now we've got an extremely large number, and we don't know anything about it. It may or may not be a prime number, but because prime numbers are the building blocks of arithmetic, it's certainly going to have a prime factor. It's a product of prime numbers. So there's some prime number which goes into this number, n factorial plus 1. And I claim that that prime number can't be less than or equal to n, because all the primes less than or equal to n, they're mentioned already in that big product of numbers up to n. So all the numbers less than or equal to n, they divide n factorial, so they can't possibly, if a prime number goes into a number, then it can't go into the next number. Like you can't have two odd numbers or two even numbers next to each other in your counting. If you're an even number, then 2 goes into you, and then to get the next even number, you add 2, right? So if you add 1, you must necessarily have an odd number. So a generalization of that idea here shows us that this prime number that we've got, it can't divide n factorial because it divides n factorial plus 1. So it must be a new prime number bigger than n. So there's a mathematical proof. So there you go. That's without a doubt the hardest part of this talk. And so now the question I want to raise is, we know that computers can do calculations very, very quickly, but can a computer understand that proof, right? And to get a computer to understand that proof, we can't just use, because that proof must be some kind of a computer program. And to get a computer to understand that proof, we can't just use any programming language. We have to use a programming language which is rich enough or expressive enough to understand the concept of true-false mathematical statements and to be able to manipulate them and produce new true-false statements from old ones. That's the kind of thing we need, because all the time we were carrying around the statements we wanted and the statements we'd proved. We were using logic to take statements we proved and deduce more statements that we've now proved. And the game is to deduce the thing we're trying to prove from all the things we have already. And a standard programming language like Python, it would not be able to manipulate true-false statements in that way. So can you get programming languages which can understand mathematics in this way? Obviously, lots of programming languages can understand multiplication, but can we get something that can understand proofs? And it turns out this problem was solved many decades ago. And the answer is yes, you can do that. And the kind of computer programs to do that are called interactive theorem provers. So let me now switch over to a terrifying looking thing. This is a modern interactive theorem prover. And I just wanted to show you what code looks like written in this theorem prover. That code there that I've just highlighted there, that is a small computer program. But that computer program corresponds to a proof that there's infinitely many prime numbers. So you see, I've proved the variant. I said this backwards E means there exists a P such that n is at least P and P is prime. And as I move my cursor down here, this thing on the right, the thing on the left is the computer program. The thing on the right is the state of Lean's brain as it's understanding the language. And as I move my cursor up, things disappear. And as I move my cursor down, more and more things appear. And these things are the hypotheses which we know. And then eventually, there we go. Like this is at the end of the proof, nothing dramatic happens. At the end of the proof, we have no goals left. So this is a computer program which corresponds to this mathematical proof that there's infinitely many prime numbers. So you don't have to understand all that. All you need to know is that there are computer programs nowadays that understand the concept of mathematical proof. So now let's get back to what I want to talk about, which is if computers now can calculate much quicker than humans, and they also understand the concept of mathematical proofs, then surely my days as a mathematical researcher are numbered. That's the hypothesis. But unfortunately, there's a catch, because part of me would love to be made redundant. That sounds like a great idea. But there is a catch. And the catch is that although now we have computer programs which can turn mathematics into a game, it can turn theorem proving into a computer puzzle game, that right now the problem is that all the best players of this game are humans. So the software is there to turn mathematical proofs into a game, but now the question is, who's going to play that game? And obviously, computers can play games, so we could try and get a computer to play this game. But right now, absolutely hands down, all of the best players of this game are humans. And so let me just briefly give you the state of the art with where we are in this area of interactive theorem provers, these programming languages, and their relation to modern mathematics. I'll give you a story from last November. Last November, 4 mathematicians, Green, Gowers, Manners, and Tao. These are not just 4 arbitrary mathematicians. So Green proved some very profound results about prime numbers, and Gowers and Tao, they've both got Fields medals. And so these people are really, these are sort of top of the range mathematicians, and they proved an open problem in mathematics called the polynomial Freiman-Ruger conjecture. I spelt Ruger wrong. I felt terrible. It's R-U-Z-S-A. They proved the polynomial Freiman-Ruger conjecture last November, and there was a certain amount of excitement in the additive combinatorics community that this conjecture was finally resolved. So the paper was 33 pages, and they put it up on the internet, and so mathematicians could start reading it and learning how they proved this theorem. But of course, the proof was completely worked out by humans. These 4 humans, they worked out that proof using pencil and paper, the traditional approach, and then they typed up their ideas as a mathematical paper, and that paper was published on the internet. And the day after it was published, one of the authors of the paper, Terry Tao, he announced that he thought it was a completely viable project to teach the entire proof to one of these interactive theorem provers. You see, I showed you the interactive theorem prover understanding a proof that there's infinitely many prime numbers, but that theorem is 2,000 years old. That's a very, very old and classic theorem. Whereas this is a theorem that was proved in November, so we can ask the question, are these systems up to understanding that kind of mathematics, 21st century mathematics? And Tao ran the entire project online, and the entire formal proof was completed within 3 weeks. And let me just show you what that thing looked like. This is a hybrid document containing. So this is a bunch of mathematics written by humans, but as well as that, there is a whole bunch of computer code that corresponds to that mathematics written in the language of that theorem prover. I could show you the computer code. I'm not sure it would teach any of us anything. It's just several thousand lines of computer code corresponding to this modern mathematical proof. And the way that it ran was that this was the proof was broken down into many, many small statements, and a gigantic graph was drawn that showed how the statements were related to each other. And a blue statement would represent something that hasn't been checked yet by the computer. And when things were checked by the computer, they went from blue to green. And as you can see, the entire graph is green now, which corresponds to the fact that the theorem has now been proved. And this was run online with lots of, there was a brief 3-week period where this graph was changing every day. There was lots and lots of things, new nodes were appearing and old nodes were changing from blue to green. And there was a lot of excitement at a certain corner of the internet where things were being managed. And about 25 people were involved. And it was sort of quite an exciting time. And the conclusion of this project was that these interactive theorem provers, now we know that they're capable of understanding the mathematics which is happening right now in mathematics departments across the world. That's what it sounds like the conclusion is. But actually, let me be more precise about what the conclusion is. It shows that these systems are capable of understanding some of the modern mathematics which is happening in mathematics departments around the world. For example, it was capable of understanding the proof of the polynomial Freiman-Ruger conjecture. And furthermore, it shows that it's capable of understanding this mathematics as long as we've got humans that are explaining it to them. It's humans writing the code, right? So in some sense, this is much less of a big deal than you might initially think. It's the computer has understood a modern mathematical theorem, but it only understood it because humans explained the proof to it line by line. So as has already been mentioned, I've just been given a 5-year research grant to teach this same system, Lean, to teach Lean a proof of Fermat's last theorem. And Fermat's last theorem is much older mathematics. It was proved around 30 years ago. But the problem is it's not 33 pages, it's 2,000 pages. If you kind of take the paper and then all the papers that it relies on. And I think it's a very interesting question as to whether we're going to be able to get computers to understand Fermat's last theorem. We're going to teach it a modern proof of Fermat's last theorem that's about 10 years old. We're not going to teach it the original Taylor-Wiles proof. We're going to teach it a sort of a more modern, streamlined proof. But that's going to take a very long time unless computers get, and unless there are sort of breakthroughs. It's going to take a very long time. So let me try and talk about these breakthroughs. This is sort of the last thing I really want to talk about. It would be, what I've tried to explain so far is there are these systems that understand mathematical proofs, and the way they work right now is that humans write the code, and then the systems check the code. The systems check that no mistakes have been made and that there's no errors in your proof and that your proof is complete. But what we really want to have is computers playing that game automatically, right? We want to remove the human from the equation and get computers to start writing mathematical proofs. Perhaps even computers could write new mathematical proofs of theorems that humans don't know, theorems that humans don't know yet. Or perhaps computers could prove great new conjectures, that kind of thing. So this software has reduced mathematics to a game. So now let's think about how good are computers at playing games. And I was a kid in the 1980s. I was very into chess. And in the 1980s, computers were not very good at chess at all. And at my chess club, people would hypothesize about, maybe computers could one day be better than humans at chess. But everyone seemed to be in agreement that this was completely out of reach because chess, you need to play an expert game of chess, you need to have a profound understanding of something which is sufficiently abstract that it's somehow difficult to explain to computers. So humans were much better at computers at chess in the early 1980s, and indeed humans remained better than computers at chess until around the mid-1990s. And then a big computer company decided to start putting money into the question. So IBM came along and they hired some people and they ran a project. They wrote a computer program called Deep Blue. And the remarkable achievement in 1997 was that their program beat the world human chess champion. And so, great. What we've learned is that if a big computer company comes along, then maybe there can be progress. And right now, many, many big computer companies have come along. And also, there are sort of secret companies working on. There are companies that don't have websites. They're little startups that they just hire people from the Lean community and get them to work on these kinds of questions. Can we get computers to beat humans at mathematics? And this is because there's been a lot of hoo-ha recently about things like ChatGPT, these large language models, and everyone thinks, well, because we got ChatGPT, maybe we're going to have AGI in the next few years. AGI means artificial general intelligence, where a computer program is just better at all humans at everything. Forget mathematics, but maybe we want some computer program that's better than all humans at everything. But one reason to focus on mathematics is that mathematics is actually a great example of if a human has to be better, if a program has to be better than a human at everything, then it has to be better. It has to be better than humans at mathematical proofs. And I think it's interesting that it's mostly tech companies trying to make a system that plays the game of mathematics better than any human. But right now, what the main conclusions seem to have been so far is that the problem of getting a computer to beat all humans at mathematical proofs seems to be really, really difficult. And right now, you can talk to mathematicians, and they say just the same thing that all the chess players were saying in the early 80s. They were saying, well, to be a brilliant theorem prover, you have to have a profound understanding of mathematics and blah, 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 blah. It's not clear how a computer can do this. And so I'm very open to the idea that in 15 years' time, all of these people will have egg on their faces, which is what happened in the chess community. But right now, we're at the stage where everybody seems to think that this problem is incredibly difficult. So I thought I'd say a little bit about why it's difficult. If we're so good, if we're so good at computers, we've got chess computers which are much better than humans. So why haven't we got computers which are much better at proving mathematical theory? Yeah, why can't computers beat humans at proving mathematical theorems? And because they're both games, right? And computers are very good at games. And the reasons that it's not difficult to highlight several reasons why mathematics might be harder than chess. And the first big difference is that chess is a two-player game, whereas proving a mathematical theorem is like a one-player game. It's a puzzle game as opposed to a competitive two-player game. And one of the ways that these computers got very, very good at chess was computers are very, very fast. And so you can just leave a computer playing chess against itself. And you can get it to play 1 million games of chess against itself in a very small period of time. And then after that experience, the computer might well have learned a lot of things about what works in chess and what doesn't work in chess. But you can't do that in mathematics. You can't get the computer to play against itself because everybody's on the same side in mathematics. We're all trying to prove difficult theorems. And another related problem, is that how does this work when the computer plays against itself? Even before somebody's won or lost, the computer seems to have some fairly good idea as to whether it's winning or losing. For example, if one computer's got a queen and lots of rooks and bishops and things, and the other player has just got a king and nothing else, then you can sort of see that the player with the king, even though they haven't lost the game yet, you can see that the player with the king is in big trouble. And the reason that's easy to see is because it's not difficult to give a heuristic score to a chess position. You can say, oh, you've got all of these pieces, so you've got a very high score, or all of your pieces are in the center, they're controlling a lot of squares, so they get a very high score. Whereas this is very difficult to do in mathematics. You can embark on a proof of a mathematical theorem, and you can sort of get halfway through, and then you could ask for your score so far, and the score is, well, you haven't finished the proof, so really your score is 0. This is the problem. It's sort of giving a score to an incomplete proof is very difficult, because to actually, the proof only has value in some sense once it's finished and it's actually proved the theorem. So I had some proof earlier with n factorial plus 1. If I'd have done n factorial minus 1, or I'd done n factorial minus n or something like this, then somehow it would have looked formally very similar, but I wouldn't have been able to put all the pieces together at the end. You really need the proof to be finished before you know whether it's once it's finished, it went in the right direction. But when you're halfway there, you've proved a bunch of intermediate results. But if the proof isn't finished, then it's difficult to work out whether those intermediate results are going to be useful or not. So let me say a word about neural networks, because that was the buzzword a few years ago. Neural networks were the thing that everyone was trying. And so you might want to just say, well, just get a neural network to work out what the next line is. And the technical response to that is that it's kind of difficult to get a neural network to do it because mathematics has got a large search space and an infinite action space. So what that means in practice is if you're trying to prove x equals y, then there's many things you can do. You're trying to prove x equals y and you're stuck. Well, one thing you could do is you could add 37 to both sides, right? And if that doesn't work, then you could try adding 38 to both sides. So there's kind of infinitely many things that you could do to change that equation a bit, all of which would be mathematically valid, right? Infinitely many. And another problem is if maybe adding 37 to both sides looks ridiculous. Well, another thing is we've got 100,000 theorems. We've got more than that now. We've got 100,000 theorems in this system. You could try applying any one of those 100,000 theorems, right? That's a big number, right? In chess, you typically have like 20 moves, 30 moves. Here we've got infinitely many moves you can make. This is the problem. Chess, you can get a certain amount of the way by just brute forcing things through. I've got 20 moves, they've got 20 responses, then I've got 20 more, and that's 20 times 20 times 20, which is 8,000, which is small. But you see, you try 3 moves ahead in a maths theorem, then unfortunately, we're incomprehensibly huge. So that's another problem as to why maths is harder than chess. But now let's step away a little bit and kind of think, well, what are computers getting good at right now? And in particular, what are computers getting good at that they can do by themselves? Because this is the problem. Computers aren't proving theorems by themselves. What can computers do by themselves? And one of the things that computers can do by themselves is they can generate huge amounts of text. They can generate huge amounts of human readable and sort of interesting sounding text. And that's these large language models such as ChatGPT. And you could ask ChatGPT to prove there's infinitely many primes. I think I won't do it now. Those of you that want to know about ChatGPT can just Google for how to use ChatGPT. But I could go to the internet now and ask ChatGPT to tell me a proof that there's infinitely many primes, and it would just write one down. It would just write down a human understandable proof that there's infinitely many primes. And the reason that it can do that is because ChatGPT was trained on the entire internet, the entire public internet. And so all it's doing is there's many proofs that there's infinitely many prime numbers on the internet, and the system just kind of looks at those proofs and just writes down a proof that sort of uses the ideas in the proofs that it was part of its training data. Right? The system is not thinking, and this is the key thing. The system isn't thinking. It's a stochastic parrot. It's regurgitating ideas. Which it's learned from humans, ironically. That's the thing. It looks like a computer doing something by itself, but that proof was written by humans. And what's worse now is that ChatGPT isn't very good. You can ask it to prove something false, and it will happily knock off a proof of a false statement. And you see, you can't do that in mathematics. One mistake, and you're dead. ChatGPT makes things up. And so the chess analogy to that, if you're trying to get ChatGPT to solve mathematics, this is like a computer chess program that just occasionally makes an illegal move. Do you see? That's not satisfactory. We can't have occasional illegal moves because now it's not chess anymore. Similarly, we can't have a random line that doesn't follow from the previous lines, because then, even though it might look like mathematics, it's not mathematics. So that's where we are at present. And what's the future is that right now people are thinking about some kind of hybrid system where you use a language model like ChatGPT, but you also use an interactive theorem prover like Lean, and you put them together into one system. So how would that work? The idea is maybe you could teach these language models. They don't just write paragraphs of English text. They write computer code. So we could train the language model to write Lean code, and then we could run that code through Lean, and Lean would say, what was correct and what was incorrect. So that would be an idea how these things could work. But even training the language model to translate human language into, unfortunately, the state of the art right now is that we're just getting these things to the point where you feed in the human proof, and the language model is beginning to become even just the very beginnings of competent at translating the human language into the computer language. But even then, it's still very poor, and that's nowhere near where we need it to be if we want to get me out of a job, because we don't want them doing stuff that humans have done already. We want them to come up with new things. And then the last thing I thought I'd mention was the AIMO prize. Let me show you the website of the AIMO. Disclosure, this is something that I'm involved with. So this was £10 million in total, $10 million in total of prizes, sponsored by XTX Markets. But this is the grand prize of 5 million. This is the thing here. This is a publicly shared model which can enter something like the International Mathematics Olympiad. This is a competition for very smart school children, and get a gold medal in that competition. So there's the challenge, and that's worth 5 million. That's worth 5 million right now, and this would already be a huge breakthrough. But when you sort of take a step back, these Olympiads, which computers currently still cannot do at all, these Olympiads are exams taken by 18-year-old children, and so they are taken by the brightest 18-year-olds in the world. But whilst the challenge of getting a computer to that level is still extremely difficult, it's still beyond the state of the art. You can also see that actually it's nowhere near the boundaries of modern research. So whilst progress is happening sort of thick and fast in this area, there's still a long way to go before computers can replace me, unfortunately, as a mathematician. And that's it. Thank you very much for your attention.
Okay, brilliant. Thank you very much, Kevin. So I appreciate that. So I put a note. Thank you, Angie, for the applause. I put a note in the chat. If people have questions, please put them in the chat box, or if you'd like to ask a question in person, please put your hand up. We can unmute you and you come onto camera. So, and as a mechanical engineer hosting an event on pure mathematics, I'd really appreciate everybody's support there. So, so please do so. So, Kevin, do you want to maybe drop the slides so
Yeah,
we can
sure.
see each other?
Let me stop sharing. There we go.
I think just
And then
get the
here's
ball
me.
rolling on the get the ball rolling on the questions. Pure maths. Sort of go back into what pure maths is. For as an engineer, I know engineering mathematics, I know applied mathematics, but pure mathematics, where do you start? And even taking it back from proving a theorem, you have to come up with a conjecture. And
Sure.
a mathematician must have curiosity. So can a computer actually get all the way back onto that left-hand side?
So yeah, I've read a question. Yeah, my argument is that here's a problem: get machines to prove theorems, and I'm arguing that it's incredibly hard. And so now, in some sense, are you asking an even harder theorem?
Yeah.
Can you get theorems? Can you get computers to actually come up with interesting questions? And here, the AI people really like this question, and there has been recent work, but I personally have found a lot of it quite disappointing, because what the things I've seen, you tend to take functions which are quite mysterious, and then you tend to be able to get the system to write down equations which are syntactically correct, like they make mathematical sense. It makes sense to ask if they're true or false, and then you could say, right, well, a computer just came up with this conjecture. But unfortunately, it's very easy to come up with difficult mathematical questions which are beyond human capabilities. But what's much harder to do is to come up with sort of interesting questions, and questions that will spur development, and questions that are sort of shed light on hitherto unsolved problems. I mean, Andrew Wiles, in his documentary on Fermat's last theorem, he talked about sort of floundering around in a room, sort of feeling the furniture and not really knowing what was going on. And then eventually, after some while of moving around, he stumbles upon the light switch, and then you switch the light on, and now all of a sudden you can actually see what's going on. And this light switch could easily be a conjecture, just as well as you prove a theorem and that resolves things, but you could easily find a conjecture which conjecturally tells you exactly what's going on. But this is again very much a human endeavor right now. Some computers, there have been recent examples of human computer collaborations that have come. There was a paper in Nature 2 years ago where some low dimensional topologists in Oxford, they suggested to some people in DeepMind that there might be some interesting questions in a certain area of mathematics, and then a neural network found a possible question but couldn't even phrase the question correctly. It was like, there should be some relationship between this number and these numbers. And then the mathematicians thought about this, and then they formulated their own conjecture, and the neural network did give it a clue, but the neural network didn't get all the way autonomously. Perhaps I've said quite enough about conjectures.
So can I ask if there are any other questions emerging? Okay, Jim, let me see if we can, if you can unmute yourself, it should work. There we go.
Yes, well, this is, I do have a question at the end, but let me say first, I think there's a lot more to be said than you have said about the relationship between proofs and programs.
Mm-hmm.
much of which you've skipped over because you're effectively doing mathematical logic, but shall we, not so much non-mathematical logic, but formalizations of logic, such as first-order logic without mathematics particularly, have been used as programming languages. And if you're in this building you inhabit, you will find that teaching proofs really comes into the first year stuff. So that's that relationship between proofs and programs is very, very rich.
Oh yes, yeah. I dismissed it as the something that was discovered in the 50s.
That's right, and then of course, being a more engineering type discipline, it's had computing science, if you like, has had phases whereby things that are aspirations in one generation, 20 years later become standard things, then don't go far enough, and they're 20 years later they're out of date. So some of those means to artificial intelligence using logic have been now discredited as being out of date. And what has caught up, of course, as you know, the things based on neural networks. One of the founders of those gave a talk to friends about 20 years ago, but never mind. And I'm certainly not dismissing at all what neural networks can do. They've gone much beyond their original conception and are managing to teach us amazing things, but there still would seem to be a tool for humans. What I was going to ask, though, about your use of the term understanding, because programs and formal proofs are based on formalizations, as you know, symbols and how symbols relate to itself. And we've learned a lot over the years from traditional mathematicians about how to manipulate and match symbols. That led to some of the early developments. But many mathematicians and lesser people like myself, if I think about, do I understand Pythagoras' theorem? Well, I understand it in certain ways. I know how to use it. But my understanding is not just the geometrical diagram, but the geometry of the proof. So I understand it in the realm of, if you like, Euclidean foundations.
Yep.
So there seem to be many interpretations of this word understanding. And I'm curious to know to what extent you are using other sorts of models for your own understanding.
Yeah. I think the only claims I made about computers and understanding were that computers didn't understand this and computers didn't understand that. And I'm just thinking about your question. I'm not entirely sure that computers understand chess, and yet they can still beat us all.
I don't actually think they do either.
Right.
But computers have proven unproven theorems, not of the sort that the real mathematicians think.
Very, very few, but yes, there are examples.
And I think it was Koestler who did a survey of mathematicians, and most of them thought geometrically rather than, if I may call it, algebraically, as you do.
Did you know it was not a coincidence that I stated Pythagoras' theorem, but I didn't prove it, And then we
Yeah.
went on to the algebraic question of prime numbers. I was just like, oh, look, here's the code.
Well, the matter can be left open, but I've touched on the subject.
Yeah. Understanding is a thorny word. Perhaps I shouldn't have used it. Well, I only said that ChatGPT didn't understand the proof of the prime number theorem. But what the question you seem to be raising is, do we necessarily need understanding in order to have progress? And perhaps we don't need that. Perhaps understanding is sort of a multi-dimensional thing. There's IQ, and then there's
I think
and then there's other things as well.
What we're very good at with computer technology is if we get back from the neural net stuff, is the manipulation of formal language, but it's formal language, not natural language.
Mm-hmm.
And so in that sense, we might have computers understanding things.
Yeah, fair enough.
But I think humans have much of their brain understanding a different model of the world.
Mm-hmm. Yeah, I think you're absolutely right. Understanding is complex.
I think the question of human understanding is the key one for making a conjecture in the first place.
Right, you're probably right. That's where conjectures are coming from.
I think that's where conjectures come from. Understanding a broader part of a field and coming up with some sort of relationship that you feel might make sense.
Right.
Well, that's kind of where I was heading with the term curiosity, because you understand that field and your curiosity takes you forward. So,
Ian has a great question in the chat.
yeah, no, I was just going to ask that.
Oh, okay,
so,
sorry. I'll let you.
just
I'll
so
let
that,
you run it. Sorry.
Yeah, so everybody knows what it is. Has a program ever produced a neater proof than humans? And it definitely isn't a daft questions. And could you talk about what mathematicians call the beauty? So there's some concepts of beauty in mathematics.
This is
So there's
very
two
hard to define. You're absolutely right, but it's very hard to define.
That term is used for programs as well.
Oh, is that right?
Oh, yes.
Yes. Talk about a beautiful student.
Oh, yes, a proof.
Beautiful program.
Mm-hmm.
Easy to read.
Programming pearls I've seen in computer science conference proceedings. So what's been happening, because computers aren't doing things by themselves, what tends to happen is you take some mathematical proof that may or may not be beautiful, and then you start teaching it to the computer, and then at some point you get to a part where the mathematics is clearly ugly, and you look at it and you think, I don't want to teach the computer this because this is going to be really painful. Like ugly arguments, sort of non-conceptual arguments can turn into really horrible really horrible computer code. And so what we've noticed has been happening is that humans, when they're faced with the problem of teaching the computer certain proof, they tend to start thinking about better ways of presenting this proof or finding the right abstraction which is going to make this proof work better. And so what happens, a particular example of it, I'll tell a story. There was a third year course that I was teaching, a third year algebra course. And there was a nice theorem in that, a very beautiful theorem statement. And I thought that I would teach the computer the proof of this, just because I was learning how to use the software. And the very first line was extremely ugly. And it really put me off teaching the first line of the proof. The statement was beautiful, but the proof was ugly. And I spent a lot of time thinking about what the point of the first line was and where we were actually going and what we should be doing instead. And eventually I came up with a much more conceptual approach. It was the same idea, but it was a much more conceptual and beautiful thing that just sort of slipped into the programming language rather elegantly. So it's not the program producing a neater proof, but it's when you get humans, when you force a human to type their proof into the programming language, then your instinct as a human is to try and tidy that program, try to tidy that proof up in a way that you might not do if all you're doing is writing a paper, where you just need to get down some proof that works. So I think it encourages you to think about mathematics in a, from a more beautiful, the aspect of it. You've got to find the right way of presenting this code, because it's going to make your life better. That was a surprise to me. That was a surprising consequence.
So Elaine's asked a question. Does Pythagoras' theorem exist in more than 2 dimensions?
Yeah, there's some statement. There's some analogous statement in n dimensions. Great.
I think one of your slides, you said it applies for all triangles, or I think it applies for all right-angle triangles.
Oh, right. Oh, you're absolutely right. Yep. All right-angle triangles. Yes. Sorry, Linda seems to be gesticulating.
Yeah, please, Linda. You can unmute. There you go. You want to unmute yourself and ask the question?
All right. Yeah, we were talking earlier about neat and beautiful proofs. I think, and what we mean by that, I mean, it's not just something which is short and snappy, but it's something which gives insight into what's going on. And is there, does Lean have that ability to have insight into a mathematical problem?
No, I don't think so. I think it's all at the minute it's a human computer interaction, and all of the insights are being had by the humans. It's at the minute it's, I mean, they do have these little algorithms. Some, you can get to a point where, well, now I think probably the rest of the argument is systematic. Now you just follow your nose and it's going to be fine. Some proofs have ideas, right? But some parts of proofs can be systematic, and there we do sometimes say, well, now can the computer just finish this off by itself? I don't even want to type in the rest of the proof. And sometimes it says, yes, of course, yes, I can do it. So then that's great. Then we could just say, now the rest is obvious, and that's the exact opposite of what you're saying, Linda. Right? That is just the sort of the bread and butter, completely straightforward.
Yeah,
completely straightforward, where you need no insights. And you need no new ideas. All you have to do is manipulate the equations in the manifestly sensible way. You've got, this has got x add 0, so let's just cross off the add 0, because obviously that makes the equation simpler. And the insights right now are all coming from humans. Is that maybe in 2 years' time, whatever, Google will just release something that's completely incomprehensible. And of course, another worry is that it generates incomprehensible proofs, right? You might end up with a system that would be some people's worst nightmare. Some system that says, oh, I can prove the Riemann hypothesis. Here's the proof. There's 1 million lines of computer-generated code. There's no insight. There's no beauty at all. But yet you run it through the program. The program says, yes, this is definitely a proof of the Riemann hypothesis. I think that would upset a lot of people. So I think what's more likely is the exact opposite of what Linda wants is going to come true.
We're starting to get into the verifying the computer, which is a whole whole game in itself. So
right. There are good answers to those questions, but let's not go there.
Just on the kind of topic, and you hinted it at the end, and I thought as you went through, you showed the example of the tau proof. You showed the human language, and then you had the Lean proof, which you didn't show us.
Right.
Which you said was go on then. Which you said would have to be written by a human. Then later on, you said that there could be some work to interpret or translate the human language proof into the
right. So here's a random. There's a random lemma, and if I click on that lemma.
You're showing us the screen with the Olympiad prize.
Yes, you're right. I've paused screen share. I know exactly what's happened. And how do I
on your other monitor?
Yeah. I don't. How do I? This has happened to me once before in my life, and I don't know how to switch it off. Let's try. Let me stop sharing and starting again. There's a little known functionality in Zoom where you can pause screen
Well, you've managed to mute yourself. I
Yes,
think.
Not our
There we go.
yes.
Right. So here is a mathematical proof. Here's a random lemma in that proof. I've just clicked on a random lemma. It's lemma 8.2, and I can click here, and there is this is the documentation of the so and now I can look at what file it's in. I can go up to the top and see what's going on. But there, if I really want to see, these are just the statements of the theorems, and then if I go to the source code, I can see the proofs of all the theorems, and there's the proof. There's a random mathematical proof.
And somebody's written that, so the
And
challenge
a
is
human has written that. But what's kind of cool is that a year ago, that was how it worked. Humans would write it. But just very, very recently, what humans have realized is that actually, if you write the LaTeX code first, and then you write the lean code under it, then these things like GitHub Copilot that are just on automatically start writing lean code for you. And they won't do the job completely, but they are getting better at the translation.
It's a bit like with kind of prompt engineering. You're starting to get ChatGPT and other models to write the prompts for themselves.
It's exactly what's happening. And the prompt here is I've just written a bunch of LaTeX. And now your job is to translate it into lean, and we're going to see progress there before too long, I suspect. But it's still humans having the ideas.
Brilliant. So time is up, I'm afraid. So it's been a fascinating discussion, certainly for myself as an engineer, and I hope the people who know a little bit more about maths have enjoyed it as well. And very much grateful to Kevin for the topic, but actually covering it in such an interesting manner at 4 o'clock or 5 o'clock on a Friday afternoon. So very much appreciate that. So
I did my best.
So I'd like to wrap up by asking people if you can unmute yourselves. We try and do a round of applause, but you can press whatever buttons rather than turning yourselves off. And so a quick thank you for Kevin.
Oh, thank you very much.
That's the friend's way. I mentioned a little bit earlier that we have a couple more events coming up in our calendar. So if I just have a quick look, I particularly like to plug our next event. So we have Professor Dan Davis. So Dan talked with us probably about 5, 6, maybe even 7 years ago. He's written. So Dan was Professor of Immunology at Imperial and went up to Manchester as Professor of Immunology. He's now back at Imperial as Professor of Life Science. He's now a prolific author, and this event actually curiously replaces the last event he was due to speak at, which was 2 days before COVID first lockdown, which we had unfortunately had to cancel. I remember I was in the SAF building, fending people off from coming in and apologising for the fact we have to cancel it. So this event, and actually it's an even newer book, so there's even more benefit of getting Dan. So that's on the 9th of May. That's an in-person event. So really keen for people to come along to that. We're hoping to have a number of copies of Dan's latest book, and obviously he'd be keen to sign those. So with a bit of luck, hope to see you there in a couple of weeks. And then we have a behind the scenes at Silwood Park. I'm guessing that's probably sold out. And then we have a virtual event a few weeks after that on the topic of CO2 and emissions. So we're kind of coming gradually to a close. Again, I'd like to thank everybody for joining us this afternoon on our fireside chat, and to Kevin for giving us the great entertainment and showing us his colourful trousers, which was much appreciated. And so with that, I'd like to close the meeting and wish everybody the best for the weekend, and hope to see you all soon. Bye bye for now.
Bye bye.
Bye bye, Linda.
Bye.
Thanks, Bill and Eddie.